this lecture, we are going to discuss the chapter 6, Electricity and Magnetism. Also, please remember to complete the homework number 7, which is related to chapter 6 and chapter 7. Benjamin Franklin is well-known as a statesman. He played an important role in drafting the Declaration of Independence and the Constitution of the United States. But also he was an important scientist. He studied the nature of electric charge and he introduced the terms of positive and negative charge. There are two types of electric charge. One is positive charge and the other is the negative charge. The negative charge is associated with the electrons in the atoms, and the positive charge is associated with the protons in the which are in the nucleus of the atom. When these two charges interact, they create an electric force. Like charges produce repulsive force, and if two positive charges interact, then they will be repelled, like is shown in this picture. But if unlike charges interact, like we show in this picture, then therefore they create attractive force. Then like charge will be repelled and unlike charge will be attracted. Then what is the electricity? Electricity is a form of energy that resulting from the existence of electrons and protons. The electricity can be statically as accumulation of charge or can be dynamically as a current. Then what we are going to study first is the electricity, the statically electricity. Then we know the electrons can move from one object to another by friction. Then what happens when this occurs? Then what happens in the nature is usually the electrons the atoms are neutral, or the compounds are neutral, means they had the same number of electrons and protons. In this case, we had for lithium atom, we had 3 electrons and 3 protons. Protons are the orange one. Then these are neutral atoms. But what happens if when the friction process occurs between two objects? Then some of the object will be lose electrons and the other object will be gain electrons. Then the object or the material that lose electron resulting in a positive charge object or material. And then we will have more positive charge than negative charge. But also can be the opposite situation. If that object or material gain electrons, then result in a negative charged electron, means has more electrons than protons. Then knowing this, we can define the electrostatic charge, and electrostatic charge is defined as excess or deficiency of electrons. Then now we can say that now we know we can define static electricity as an imbalance of electric charge in any material. And what happens in case of the static electricity? That charge will remain in an object, or will be confined in an object until this charge are able to move away as an electric current or electric discharge. And this is what happens when if our body get charged, then if we touch the knob of the door, then what we will feel like some shock. As this is happening, is our body is electrically discharged in that moment. Yes. There are three ways the charge can be transferred. The charge can be transferred by friction. Yes, by friction. We already discussed this one. Then this happens when the electrons pass from one object to another. The charge can be transferred by induction, and this we will discuss in detail is happening because of the redistribution of the charge in a material, or by contact. Yes, and if we had any material or any object that is charged, and we touch that object, then we will be charged, as is shown in that example. Yes, that is that example. How the charge is transferred by friction. Then in this example is before we comb our hair, what happened is our hair is neutrally charged, means equal positive and negative charge, and the comb also is neutrally charged. They had the same number of positive and negative charges. But what happened when we comb our hair? Then in this process, the hair will lose some electrons, and then will be positive charged. Yes, we will lose, for example, this is just an example, one electron, and then will be positive. The net charge will be positive too. But in case of the comb, it will be gain electrons, then will be charged negative. Yes, will be had negative charge, negative net charge. Then we can say the hair and the comb, they are electrostatic charge. And this is because one is charged, when it's the comb is charged negative, and the hair is charged positively. Then what happens is they will attract, they have opposite charge, then the comb will attract the hair. In this sequence of experiment, then we will see how the charge is transferred by both for two mechanisms. One we can see by friction, and also we can see by induction. Let's start. Then what happened here is that person is rubbing the tube using a piece of fabric. In this process, the charges are transferred from one object to another object. And after that process, finally the tube is charged negative, then has some has excess of electrons, and the piece of fabric is charged positive, then they had a deficiency of electrons. Then here we can see is there are transfer of charge by friction. But now what happens if he brings the tube closer to the papers? Then when that person bring the tube closer to the papers, because the tube is charged negatively, that induces a reorganization of the charge in the paper. Then because the positive charge is attracted by this negative charge on the tube, then the charge in the paper will be reorganized, rearranged in this way. And this is why, because the tube is positive, the tube is negative charged, and this side of the paper will be positive charged, then that tube will be attract the papers. Remember, positive and negative charge they attract, and this is why the tube attract the paper. Then in this case, we had a transfer of charge by induction. In this video, this is a short video, I want to show the real experiment using the electroscope, in which also is showing how the charge is transferred by induction.
Is the electroscope.
These devices were originally designed to detect and measure static charges. This one has two pieces of aluminum foil hanging down from wires attached to a bolt, comes up through the center, and has a large metal ball sitting on top of it. Let's try with a negative charge. Once again, we have a polarization of the electrons away from that negative charge. Now let's try with a positive charge. In this case, the electrons of the metal move towards the positively charged glass.
Now we want to define what is the fundamental charge. The fundamental charge is the electrical charge that corresponds to 1 electron. Then the charge for 1 electron equals to 1.602 10 to the power minus 19 coulomb. And the symbol for the coulomb is the letter C. Yes, in the same way the velocity, the units is meter per second, then the units for charge is coulomb. If we want to calculate the total electric charge for an object or a material, then we need to multiply the number of electrons times the fundamental charge. Then remember, the fundamental charge is the charge of 1 electron is equals to 1.602 10 to the power minus 19 coulomb. Then we say when two charges interact, they produce an electric force, and that electric force is attractive if the charges are unlike, and this force is repulsive if the charges are like. Now we want to know how to calculate that force. Then remember, we study the gravitational force, and in case of the gravitational force, let me write in this part here. The gravitational force was G constant mass 1 times mass 2 to pi. Then we can calculate the gravitational force if we multiply the constant of gravitational times the mass of the object 1 times multiplied by the mass of the object 2 divided by the distance between the objects. Then using the similar equation, we can calculate the force, the electrical force between two charges. Then in this case, we replace the G by the K. K is a constant, and the value of this constant is 9.00 10 to the power 9 newtons meter squared divided by the coulomb square. Instead of mass, we had the charges 1 times charges 2, and then divide by the distance between the two charges. Yes, the distance between the charges. Then how we can calculate this force? We need to multiply the magnitude of the charges and divide by the distance between the charges. Divide by the square of the distance between the charges. And of course, we cannot forget to multiply by the constant of proportionality, K. this equation, the equation we use to calculate, we apply to calculate the force between two charges is known as Columbus law. Then let's now analyze this equation. Then what happened is we can see, yes, is we just apply the line testing. We can see the force is direct proportionally to the product of the electrical charges, but is inversely proportionally to the square of the distance. Means more charge, if the magnitude of the charge is increases, then the force also increases. But the relation with the square of the distance is inverse. Then if the distance between the charges increases, the magnitude of the force will be decrease. In this video, we are going to see what is the effect of the electric force.
It's actually a very good insulator. In this case, I have an 8-foot 2x4 hanging from the ceiling. And the charge on it is neutral, but we're going to see if we can move it with a static charge. Now we'll get a nice charge on our PVC pipe here and see if we can move it. Okay, there it goes. See if I can reverse directions.
Then in this video, we can see how if we can transfer more charge to the plastic tube, then we can get larger force, as we are able. That in this case, he was able to move the plank. Also, you can see how the plastic tube must be close to the plank in order to get a larger force, a larger effect, because less distance, more force. In this example, we want to calculate the magnitude of the force, of the electrical force, between one rubber balloon, which has a negative charge equals to 3.00 10 to the power minus 14 coulomb, and if the distance between another balloon which has negative charge of 2.00 10 to the power minus 12 coulomb is the distance between these two balloons are 0.0200 meters, means 2 centimeters. Then we want to calculate what is the direction of the force between the balloons and what is the magnitude of the force. Then the first thing to know the direction, we need to pay attention to what kind of charge we had, what kind of charges we had, because both charges are negative. Then we know if they are like charges, the force is repulsive. Then in this case, this will be the direction of the force in this way. Now we want to calculate the magnitude. To calculate the magnitude of the force, we will use the Coulomb law. And let's try to find the values. Then we know the K value, the constant of proportionality. Then now we need to know the charges, what is the magnitude for the charges. Let me write this one. N is Q1 equals to 3.00 10 to the power minus 14 coulomb. The magnitude for the other charge is 2.00 10 to the power minus 12. And the distance between these two, because the constant of proportionality as meters, yes, as one of the units, then we want the distance in meters, and it's 0.0200 meters. And I think will be easier when we are doing the calculations if we write this in scientific notation. Then it's 2.00 10 to the power minus 2 meters. Yes, we move 2 places. And now we have everything we need to calculate the force. Just we need to apply the equation. Then the force equals K value is 9.00 10 to the power 8 Newton squared times the charge 1, 3.00 10 to the power negative 14 coulomb, times the second charge is 2.00 10 to the power minus 12 coulomb. Everything is divided by the distance, but just remember is the square of the distance squared, and it's 2.00 10 to the power minus 2 meters, but square. Then this is the force. This is how we need to calculate the force. Force equal. This is the electrical force. Now the electrical force, let's multiply first the charges to see how we can cancel out the units. That's how we can cancel out the units. And let's multiply the charge first, the charges, 10 to the power 9 Newton. Now we multiply the charges. If we multiply the charges, we can multiply just the numbers. 3 times 2 is 6. Is 6.00. 10 to the power. Because both are negative, the exponents both are negative, we need to add the numbers together and keep the negative sign. Coulomb times coulomb will be coulomb squared. Divide by 2.00 10 to the power minus 12. Here, sorry, let me do something here. And let's square the number. Then 2 times 2 equals to 4. Remember, to square, if we had power of a power, we just multiply the powers. 2 times 2 is 4, but this is negative. And minus 2 times 2 is negative 4, and we have to square the units also. Now we can see this column cancel out with this column square, these two cancel out, and meters square cancel out with this meter square. And finally, we had the answer in newtons, and this is we expected, as this is the unit we expected because it's a force. If we multiply the denominators, we will have 9 times 6 is 54. Keep the 3 significant digits. Now in this case, we want the exponents is positive, the other one is negative, then we need to subtract these exponents together and keep the negative sign because it's a larger number. Negative 17 newtons, this is 17. Okay, divide by 4, 10 to the power minus 4. Then if we divide the numbers, 54 divided by 4 equals to 13.5. negative 17. Remember, we subtract the exponents if we had division. This one minus this one, then minus 4. Yes, because this one minus this one, but the exponent in the denominator is negative. And finally, here we had positive. And we had positive. Negative times negative is positive. Then the force equals to 13.5 10 to the power negative 13. Yes, negative 13 newtons. This is right, but if you want to write in scientific notation, remember we move to the left, we need to add 1. Yes, we move one place, we need to add 1. Then finally we had 1 point. Finally we had the force equals to 1.35 10 to the power minus 12 newtons. And this, yes, it's like a long problem, but just you have to be careful in each step with the math. Yes, this is what you need to be careful. In this slide, we want to discuss the concept of electric field. And the electric field is related to the space around the electric charge. And what happens is, if there is an electric charge, the condition of space around that charge change. And how we can draw the electric fields? Then we can use lines and we can use arrows to indicate the direction of this electric field. This kind of diagram is called the electric field lines. If we had one charge, we had insulated charge, either negative or positive, we can represent the field as a straight line and indicate it in these two figures. If the charge is positive, the arrows will be pointing away from the charge. If the charge is negative, then the arrows will be pointing toward to the charge. But if there is more than one charge in the region, like in the cases we had in here, then the electric field, the lines of the electric fields are not a straight line. They will curve. And how they will curve depend of the kind of the charge we have. And if they are positive and negative, if they are unlike charge, then we will have this kind of diagram. Remember, if we had unlike charge, they attract. Yes? And always the arrows will be pointing from positive to negative charge. But if we had like charge, like in this case, to both negative or both positive, then remember they will repel, and this is why we have this kind of diagram. In this case, there is no connection between the lines of the two charges. In this video, we are going to observe how the electric charge can change the space around them. Means we are going to observe the effect of the electric field.
The Van de Graaff generator is a must-have when teaching electrostatics and the electric field. For example, you can use it to show that the electric field is higher near pointy edges than rounder ones. You see, it is the electric field that ionizes the air and makes lightning. A pointy edge can do that easier because the electric field is higher. Notice also that these lightning rods are connected to the ground. Of course, you can also use the Van de Graaff generator to demonstrate radial electric field lines. For example, you can tape streamers on the top of the Van de Graaff and they will point radially outward. Or you can use a human
Find a long-haired human and have her stand on a milk crate for insulation. Remove all metal such as rings and glasses and zippers, and with any luck and dry weather, her hair will stand up. Another way to demonstrate electric fields with the Van de Graaff is to hang a string over the charged dome like you're going fishing. Watch as the charged string is amusingly repelled by the electric force field. But I think the most convincing...
And in this video, we can see how the hollow metal glove, which is charged, can change the space around it. Means that hollow has electric fields around it. Another concept we want to discuss is the electrical potential, or also is known as voltage, and the symbol is the V. Then we know if there is a charge, the space around of the charge change. Means if there is a charge, there is also an electric field. Then what is the electrical potential is how much work we need to do if we want to move one charge in the electric field of another charge. Is how much work, yes, voltage is how much work we need to do to move this charge into the electric field of another charge. And the voltage we can calculate how much work we need to do, divide by the magnitude of the charge we want to move. Then this is the way how we can calculate the voltage or the electrical potential, is the work divided by the magnitude of the charge. Then we know the work, the units for work is joules, yes, it's joules, and the units for the charge is coulomb. Then the joules per coulomb is defined as volt. Then one joule divided by 1 coulomb equals to 1 volt. And these are the units for electrical potential or for voltage. Is volt. Then the simple electric circuit has an voltage source that can be a battery, has a device in which the work is done, can be a lamp, and also has some continuous pathways in which the charge can move through these pathways. Usually is a wire. Then how we can define the electric current? The electric current is how much charge per unit time pass through these wires. Yes. How much charge per unit time pass through these wires. The symbol for electric current is I. Then we can say the electric current is equal to the charge or electric charge divided by the time. Then how much charge per unit time. Then the equation, remember the electric charge, we can represent the electric charge by Q. Then the current is Q divided by the time. Then now let's check the units. The units for charge is coulomb. The units for time is seconds. Then coulomb divided by seconds correspond to the ampere or amp, or we can use just A. Then both abbreviations are right. Yes, ampere or A. Then the units for currents are ampere, and this equals the 1 ampere or 1 amp equal to 1 coulomb divided by 1 second, or 1 coulomb per second. Depend how efficiently are the materials to transfer electrons. Then we can classify the materials as conductor or insulators. Then conductors are materials that can move electrons easily. Then good conductors are usually metal. This is good example as conductors, and they can move electrons easily. But that materials that don't move electron easily are known as insulator, then they are not good. They are not good conductors. They also as that materials are also known as non-conductors. Now let's do this example just to be more familiar with the equation. And we know the current, we can define the current as the rate of charge per time. Yes, the rate of charge is how much charge per time. Then in this example, we had an electric current through a wire is, then the electric current through the wire is 6 coulomb. Then by the units, we know this corresponds to the charge, yes, because this is the charge. Then we have the Q value equals, let me write here, Q here. The Q value equals to 6.00 coulomb. Every 2 seconds, then the time is 2 seconds. Then what is the magnitude of the current? And current then is charge is 6.00 divided by the time, it's 2.00 seconds. Then the current equals to 6 divided by 2 is 3.00 coulomb per second. Then this means each second, yes, each second flow 3 coulombs, yes, 3 coulombs is the charge correspond to 3 coulombs. Then this is why is the current, we can define the current as a rate of charge, yes, how much charge per time. And remember this coulomb per second correspond to the amp. Yes, this are how we define amp. Also, it's okay if we just write like that. Yes, both answers are the same thing. The next concept we want to discuss is the electrical resistance. Then the electrical resistance is related to the opposition to movement of electrons. Then there are some materials that have the property to reduce the current. Yes, to reduce the current. Then how we can define the resistance? Then the what happens if we apply some voltage and we can measure large value of current, mean the resistance is low. Yes, the resistance of the material is low because we had high current. But if we apply some current and we have if we apply some voltage and we have low resistance value, we can say the resistance is high. Yes. Then high current, low resistance, low current, high resistance. And this is why the relation between resistance and current is inverse relation. Yes, it's inverse relation. If we keep constant the voltage, the resistance and the relation between resistance and current is inverse. This is, we have this equation. We can define the resistance as the ratio between voltage to current. Yes. And this is why we can the resistance as the ratio between the potential difference of voltage is the same thing between 2 points and the resulting current. Now let's check the units. What we had on top is volt, yes, is the units for voltage. What we had in the denominator is the is ampere or amp. And the ratio between this voltage over ampere has a special name, is the units for resistance, which is ohm. And the symbol is the omega. Yes, is the Greek letter omega. Then again, the resistance is defined as the ratio voltage to current. The ionics are both volt because we had voltage, amp because we had ampere, we had current in the denominator, and this has a special name is ohm. And the ionics for resistance is ohm. Now we can rewrite this equation. That's right here. We can rewrite this equation. We have resistance, voltage. If we multiply on both sides by the current, this cancel out, and we can rewrite this equation like yes, this is we have here. Then this equation, which is basically the same we had here, but when we write this equation like that, is known as Ohm's law. And Ohm's law shows the relation between voltage, current, and resistance. Unless I want to discuss this graph here, voltage versus current, then what happens if we can rewrite this equation, yes, like it's the same thing, yes, just we change the order of the factor, then we had basically the same equation. And if we rewrite this equation like that, and we plot voltage versus current, yes, we had voltage here, this is voltage, we had current here, yes, we had voltage in y and current in the x direction. Then and the resulting graph is at a straight line as we had in this case. Yes. Then the relation between voltage and current is direct proportional. And what happened is, if we had this equation, we had slope. And we can see the slope of this line correspond to the resistance. Yes, we had y equal plus b. Y is the voltage, x is the current, then the slope must be the resistance. And the slope of the, if the relation between voltage and current is a linear relation, then the slope of this graph corresponds to the resistance of the material. Then I mentioned this one because in the final test, I will give values for voltage and current, and you have to calculate the resistance of the material. To do that, you have just to graph voltage versus current and calculate the slope of that line. In these problems, we want to apply the equation that correlate resistance, voltage, and current to solve these two problems. Let's read the first problem and try to solve. In the first problem, we need to calculate the resistance of a circuit with 120 volts and 4 ampere. And we want to calculate the resistance, then we need to apply this equation. You can see these two equations are basically the same equation, just is written in different way, but these two equations correspond to the same equation. And let's solve the first problem. Then we need to calculate what is the resistance if we know the resistance, this circuit had 120 volts, then you know the voltage, volts, and has 4 ampere. 4 amp. Then this case, just we need to divide, yes? Resistance equals to volts divided by the current. Resistance equal to the volt divided by 4.00 amp, and the resistance equals to 30. 30. We have 3 significant digits. We want to keep the 3 significant digits. Volt amp. Then remember, volt over amp equals to ohm. Ohm is the unix for the resistance. And let me write here, resistance equals to ohm. This is how we define ohm, is 1 volt divided by 1 ampere. And now let's solve the problem, the second problem, number 2. And 2. And we want to calculate what is the current. Yes, what is the current? And we don't know what is the current in a 60 ohm resistor. Yes, how much current passed through 60 ohm resistor? Then we know this is the resistance, 60 ohm resistor, when the potential difference across that the resistor across it is 120 volts. And if the voltage is 120. And we can use either the first equation or the second equation because they know they are the same equation. And in this case, we need to solve for the current. It will be easier if we use the equation in the second form. Then voltage equals to the, and we need to solve for the current, then we divide by the resistance on both sides. And we have here current equals to the voltage divided by the resistance. Now we calculate the current equals to, and we had voltage is 120 volt divided by the resistance is 60 ohm. And we can write here this one like 120 voltage divided by, but ohm, remember ohm is volt by the ampere. Then the current will be 120 divided by 60. But let's keep the 3 significant digits. Now we know the answer must be amp because this is the unix for the current. Let's check here the unix on this side quickly. We had voltage on top, and we had in the denominator voltage divided by amp. And we know we can change the division by multiplication and just flip the fraction, just flip the unix by voltage. Then voltage cancel out and we had the unix amp. And this is why the unix here must be amp. And this is the current passed through this resistor. Yes, it's 2 amp. And now we want to define what is the electrical power and electrical work. We know already defined the electrical work, but now we want to define also electrical power. Then just review what we say before. The simple electric circuit has 3 parts. One is the voltage source, can be a battery, an electrical device which the work is done. Yes, is the light bulb in this case, or can be a lamp, can be a motor, and conducting wires which is used to the electrons move, yes, to the charge move. Then what happens is the voltage source creates a different potential difference. This voltage source create a potential difference, and this potential difference is doing work on the ball or on lamp yes, whatever we had here, to move charge to a higher potential. Yes, this creates some potential difference to do some work, and that is to move charge to a higher potential. Then remember, we define the power as how much work some device can do in some time. Yes, is how much work can do in some time. Then this is power is the rate of work, or just the work divided by the time. And it's how we define power as before. Then now the voltage, we know voltage equals to work divided by the charge. Is how much work, remember how we define the voltage is how much work we need to do to move one charge in the electric field of the other charge. Yes. Then this is why voltage is work divided by the charge. And we can solve for work in this case. Yes, we have here, I just want to write in this way. Let me give some space here. Then we had here voltage. If we want to solve for the work, we need to multiply by the charge on both sides. Here. And we can cancel out, and finally we had work. And this is what we had in this line, yes, here. And this is the electrical work. This is the electrical work. And now let's replace the electrical work into this equation, into the power equation. Yes. Then work equals to charge times voltage. Then just replace work by this. And this is we did in this line. Yes. Then power equals to the charge time volts divided by the time. But we can rewrite this equation. What we had here is, let me write. Divided by the time. Then we can rewrite this one like T times voltage. Yes. Then charge divided by the time multiplied by the voltage. And we had the same thing. Yes, we rewrite this. But we know the charge divided by the time correspond to the current. Yes, this is how we define current. It's how much charge per unit time. Yes, times voltage. This is we had here. This is how we can define the electrical power. Now the electrical power, we can calculate the electrical power if we multiply the current of the circuit times the voltage of the source. Yes, this is how we can calculate the electrical power. Now, because it's a power, we expected the units in watts. Then let's check if the units are watts. And what we have here is the units. This is current. Then is the units for charge is coulomb. The units for time is second. Now the units for voltage. Then the units for voltage, remember, is voltage is work divided by the charge. Then for voltage, yes, for voltage must be joules, the units for work, divided by the units for charge, which is coulomb. Then this is very right in here. Yes, is coulomb per seconds times joule per coulomb. What happened with the coulomb? They can cancel out. Yes, they can cancel out. Here they cancel out. And finally, what we had is joules per second. And this is how we define watt. Yes, joules per second. How much work per unit time. Yes, units of work divided by the units of time. Then we can see then the units are consistent, yes, this correspond to electrical power. Then how we can calculate the electrical power? Just we need to multiply the current times the voltage. And in these two problems, we want to apply the equation of the electrical power. Then remember, the electrical power is current times voltage. Then in the first problem, we had an electrical motor that draws a current of 14 amp in a 240 volt circuit. Then we want to calculate what is the power of the motor. Yes, this is we want to calculate the power. Then the first problem. Then we know the current is 14, and let's write in the way we did before. The voltage is 240 volts, and we want to calculate what is the power. Then in this case we had power equals to the current times the voltage. Then power equal to the current will be 14 amp. The voltage is 200 volts. And if we multiply these two numbers together, then we will have this 3,360. Now what units we expected here? Because it's a power, we expected watts. And let's see, review again this one. We had ampere. We know ampere is coulomb per second. Let's write better this. See if I can write. Then we know amp, maybe here, coulomb per second. And we know the voltage is joules per coulomb. Then this cancel out, and finally we had joules per second. And finally, the power is watts. This is the answer. Next, second problem. And in this case, we had a light bulb with a resistance of 10 ohms, and the resistance equals to 10 ohms. Allows a 1.2 ampere current, and we know this one corresponds to 1.2. Let's write this. amp. 1.2 current to flow when connected to a battery. Then what is the voltage of the battery? Yes. What is the voltage? And we need to calculate the first part. What is the voltage? And we know we can calculate the voltage is the current times the resistance. Then yes, we calculate will be 1.2 amp times the resistance, and the resistance is 10 ohms. Then the voltage equals to 1.2 times 10 will be 12.0, and because it's voltage, we expected the units in voltage. Then just remember we had here how I cut right here Ampere is here. Let me write here the ionics. And ampere. Then we had here resistance. We had ohm, but ohm is volt by ampere. Then this cancel out, and the ionics is in volt. This is we expect as the here is just to check the ionics. Now we need to calculate what is the electrical power. What is the power of the light bulb. Then to calculate the power, we need to multiply. Then the current is 1.2 amp times the voltage, but the voltage is 12 volts. Yes, here, let me write 12 volts. Then the electrical power, if we multiply these numbers together, will be 14.4. And we did here, we know ampere times voltage. We had the same thing here. Ampere times voltage correspond to joules per second, which is watts. As we already explained here again the ionics. And we know ampere times voltage correspond to watts. Yeah, this one is the answer. That's something like that. Let's move to the next slide. And in this slide, I want just to show when we had this unit kilowatts hour, this is the ionics is given how much we consume energy in our home. Yes, in the electricity bill, we had this ionics. Yes, how much energy we consume per month. Yes, in kilowatts hour. Then just I want to show you this ionics correspond to energy. Yes, this if we had this ionics, I will just write here. It's kilowatts. See if I can. Kilowatts per hour. Then just remember, kilo means 1,000. Yes, kilo means 1,000. Unless I will write here kilo means 1,000. Watts is the ionics for power. Power is work for unit time, means joules per second. Yes, let me write better this. Kilowatts per equal 1,000 watts. Watts means joules per second. And we know in 1 hour we have, because we want the same ionics, and we know in 1 hour there are 3,600 seconds. Yes, and right here, and 1 hour equals to 3,600 seconds. Then this is joules. Oh my god, it's hard to write. It's joules per second. Then these seconds cancel out, and finally we had in joules. This is the ionics we expected, because this we are trying to show this the ionics correspond to energy units. And if we cancel out the seconds, finally we can write this one let's write first in the standard notation. Then it's 300 and 1, 2, 3 more zeros. 1, 2, 3. It's a huge number. Yes, it's 3,600,000. Yes, it's big number, joules. And we can write this one in scientific notation. And finally, we got 1 kilowatts hour equals to 1, 2, 3, 4, 5, 6. 3.6 10 to the power 6 joules. Yes. Then 1 kilowatts hour equal to 3.6 10 to the power 6 joules. Then this units is just, I want to show this units correspond to energy units. The last thing we want to discuss in this chapter is few concepts about the magnetism. Then magnetism and electricity, they had some similar feature. And in the same way we had a positive charge and negative charge in electricity, and we had also we had in magnetism, we have magnets that had North Pole and South Pole. And in the same way we had positive and negative charge in magnetism, we had the magnets that has North Pole and South Pole. Then also in the same way, unlike charge they attract, also when we had two magnets, then South and North Pole they attract. And also in the same way, electrical like charge, electrical charge they repel also. It's the same pole in magnetism they repel. For example, north and north they repel. Then like poles repel. Then here also we can see is in the same way most of the properties, the electrical properties that concentrate close to the charge. Also the same happen here. Is most of the properties are concentrated in the poles. But one thing that is different to the electrical charge is the magnetic poles always come in pairs. And what happened if we had a magnet and we cut this magnet, we cannot divide the North Pole and the South Pole. If we cut that magnet, we will have a new magnet with North and South Pole. Then the separation of the pairs into the single poles called monopoles had never been accomplished. Then always the magnetic poles come in a pair. Yes? Also, in the same way, if you had a magnet, if you had an electrical charge, this charge changed the space around, yes? And this is we call the electric field. Then in the same way, if you had a magnet, that magnet changed the space around it. Then this space is called the magnetic field. And also, we can represent the magnetic field using the field lines. Yes, this is a real picture. We had here a magnetic field. We can see how this rearrange. Yes, this iron fillings they rearrange because of the presence of this magnet. Yes, it changed. This magnet changed the space around. Yes. Then these lines is forming here correspond to the lines of magnetic field. And we can see the lines at close to the magnets because here the magnetic field is greater. And they become apart when they are far from the magnets. Yes, for example, in this place. Then this is the animation. Always the magnetic lines, the magnetic field lines is go from the north to the south pole. Yes, in the same way in the electric charge, the lines go from the start in the positive charge and end in the negative charge. Then here start in the north pole and end in the south pole. Then here is how we can map, yes, the magnetic field around a magnetic bar. Yes, this is how then the lines start in the North Pole and end in the South Pole. One more thing is we can explain here is the difference between the geographical poles of our planet, of the Earth, and the magnetic fields of the Earth. Then they are not the same. Then let's explain why. Then we know the Earth the Earth has a big magnetic field due to the that electric currents that circulate in its core. Yes, this is magnetic of metallic materials in the core at huge temperature. Yes, the temperature in the core of our planet is huge temperature. Then everything is molten there. Then this metal that is circulating in the core of the Earth, like nickel, iron, this creates the magnetic field of the Earth. Yes. Then what happened is, this is why the Earth has a magnetic field. Then we know this is the North geographical pole. Yes, it's the North. We are in the North, and this is the South geographical pole. And what happened if we had a compass? Then the compass will be point to the north in this direction. Yes, this is the north because this is the geographical north. But if this compass is point to the north, yes, it's because it's attracted by the South Pole. Remember, North Pole is attracted by the South Pole. And like poles, they attract. And this is why if this compass the north is pointing in this direction, if this North Pole is attracted in this way, then the magnetic pole of the air, the North geographical pole of the air must be the South magnetic pole. And this is why the North geographical pole corresponds to the South magnetic pole. And in the same way, the South geographical pole corresponds to the North magnetic pole. In the next slides, we are going to discuss the relation between the electric currents and magnetism. The first person that studied this phenomenon was Hans Christian Ørsted, and he was doing an experiment. He applied some voltage through the wire, and when the current passed through the wires, what he observed was the magnetic compass was close to the wires, was deflected, was moving. Then what he concluded is the electric currents produce a magnetic field. And later, the scientist, he observed when the wire was formed into loop, like this one is, you had a wire, you had the magnetic field, and when this is formed into loop, the lines of the magnetic field concentrate, then you had a large magnetic field. Then what happened when instead of you had just one loop, you had many loops of the wire, and you will have more concentration of magnetic field lines, then you will have higher or large magnetic field. And when many loops of wire is formed into cylindrical coil, is called the solenoid, like we had in this case. And what happened is when we had the solenoid like this one, and we apply the voltage between the ends of the solenoid, is you will have this solenoid it will act as a magnet. And this this phenomenon is called electromagnet. Yes, you had a magnet because you apply some voltage through these 2 points, and this generate current through the solenoid, and then create a magnet. And when you had a solenoid, yes, when you had a solenoid and you apply a voltage, you will create a current, and that current will create a magnet effect. Yes? And when you have this electromagnet, is the behavior of this electromagnet is exactly the same as if you had a permanent magnet, if you had a real magnet. Yes, the effect is the same. And this effect is really important because now we use that effect for many applications. One of the few applications we can mention is, for example, electromagnetic switches, speakers, microphones, memory sticks, magnetic resonance imaging, fast trains. This is few of the examples in where this effect, the electromagnetic effect, is applied. Also, another application for this effect, for the electromagnetic effect, is the electric motors. The electric motor is an electromagnetic device that converts electrical energy into the mechanical energy. Then the electric motor has two basic parts. One is stationary magnet. We had one permanent magnet. It's like a bar. This is a bar magnet, magnetic bar. This is the stationary magnet. And we had electromagnet armature. Yes, we had this electromagnet armature. And what happened is, remember when we apply some voltage through this wire, then we create a magnet. Yes, we create a magnet. Then because we had here permanent magnet, we had another magnet. The interaction between these two magnets made this armature move. Yes. Then this is how we can use the motion, yes, of the armature to do some work. And this is why we convert electrical energy, yes, we apply here, into the mechanical energy. Then we can use the motion of this armature to do some work. The other is the opposite effect. Is how the magnetic can induce some electric effect. Then in this case we had a loop of wire, yes, and we don't apply any voltage to this. We don't apply any energy to that. Yes. We don't. You can see there is no net connection here. But what happens is when this magnet is moving through the loop of wire, then we can see some voltage is generated, and this voltage is called the induced voltage, and the resulting current is called the induced current. And this is how the magnetic can induce some electric effect. Yes. And just due to the motion of this magnet through the loop, to these loops, we can see there is that result in some current. The magnitude of the voltage we can get here depend on the number of loops, how many loops we had in the loop of wire, how big is the magnetic field, the magnitude of the magnetic field, the magnet we had here, yes, the magnet, and how fast we move this magnet through to the loop of wires. One of the applications of the electromagnetic induction is the generators, and the generators is a device that converts mechanical energy into the electrical energy. Again, here in this case, we don't have any electrical connection. However, we can see light in this bulb. Then the reason is we can induce some voltage due to the magnetic effect. And in this case, we had a permanent magnet. Is this we had here? This is the permanent magnet, and we had a loop of wire. And what we are doing is, instead of move the magnet like we did in this case, we are going to move the loop. Then we move the loop, and the interaction between these two magnets, as the magnets in the loop and the permanent magnet, induce some voltage, and this is why we can see the light in the bulb. And this is, but we need to move the loop, and this is why mechanical energy, yes, because we need to move, is converted into the electrical energy. Then just to summarize, the motors convert electrical energy into the mechanical energy, and generators convert mechanical energy into the electrical energy. And in this table, we had the summary of the different quantities we studied in this lecture, and the equation and the respective units for each quantity. And this is all I had for today. Bye.